Hello friends, welcome back to another tutorial in network analysis and synthesis. This is going to be my first tutorial in 2020, so I'd like to wish all my friends and viewers a very happy new year. So let's get straight into the maximum power transfer theorem for DC networks today. The statement for this theorem says that if a resistive load is connected to a DC network, it receives a maximum power when the load resistance is equal to the internal resistance of the source network as seen from the load terminals. Now let's understand this statement because it's not very easy to comprehend this statement as it is. If we have a network and we reduce that network into its Thevenin's equivalent circuit, so this statement says that this load RL will receive maximum power if this load resistance is kept equivalent to the internal resistance of the circuit. Or in other words, if this RL becomes equivalent to RTH, we are sure to receive maximum power at the load. If we wish to calculate the current in such a circuit, we'll get current to be equivalent to V0 upon RTH plus RL. Two resistances in series, and the derivation of this becomes pretty easy because we wish to find power delivered to the resistive load, which is I square RL, and the current in this circuit will be V0 upon RTH plus RL. So substituting the current's value here, I get current square into RL. And what would be the condition for the maximum power to be delivered? The condition for the maximum power to be delivered is by varying RL. So max PL can be delivered when the derivative of PL with respect to RL becomes 0. So this will be the starting point and the rationale behind the maximum power transfer theorem. Although the statement clearly says that RTH should be equivalent to RL, we are proving this now. So the current in such a circuit will be this, and the power in such a circuit at the load will be this, and it will receive its maximum power when we vary RL, and PL can be maximized by keeping dPL upon dRL is equivalent to 0. And so we simply have to perform some mathematical calculations that you can note down from this derivation. You could pause the video and note this down. I'll quickly browse through this. So this becomes the value of dPL upon dRL, and clearly if we wish this to be equivalent to 0, we'd need to keep RTH to be equivalent to RL. So you could pause the video here and get to this point of derivation, and after this you simply need to find the condition where the derivative of PL upon with respect to RL becomes 0, and that will happen only when RTH is equivalent to RL. Clearly see that the numerator will become 0 when RTH minus RL is 0, or RTH is equivalent to RL. And this gives us some very important key terms. We see that when RL is equivalent to RTH, this is known as a matched system. So this is a keyword. So it's a matched system when RL is equivalent to RTH. And what will be the maximum power? Because now that we've determined that if RTH is kept equivalent to the load resistance, we get the maximum power. But what will be the maximum power? So we've seen that the maximum power will be V naught square upon RTH plus RL is now substituted as RTH, and this RL is also substituted as RTH. So we get V naught square upon 4 RTH. So this is also very important result for the examination point of view, that the maximum power delivered is V naught square upon 4 RTH. And we'll see a sample question here. A sample question will look something like this. You might be given a network where you'll be asked what should be the value of RL so that the maximum power is delivered to this load. So if you examine closely, it is not asked to find the maximum power. It is simply asking you to find the value of this load resistance for which the maximum power will be delivered. So you simply need to find RTH. You do not need to reduce this circuit into Thevenin's equivalent circuit and find the current and then eventually the power, but so you simply need to calculate the value of RTH, which is one of the steps of finding a Thevenin's equivalent circuit. So RTH is simply removing all the independent sources. So we have two sources here, and those two sources are voltage sources, so we short them, and we see the resistance from the load. So we open the load and see the resistance from here, which is 1 parallel 2 in series with 5 and then parallel 1. So we get 0.85 as our RTH. Now if we keep our load resistance to be equivalent to 0.85 ohms, we are sure to get maximum power delivered to this load. So this theorem is super important from the point of view of examinations and competitive examinations. Many a times you will be asked to find the maximum power delivered at the load, so you need to find RTH and VTH both and then calculate the maximum power delivered. So I hope this quick introduction tutorial to the derivation of maximum power transfer theorem was of help. If you liked the video, give it a thumbs up. Consider subscribing to the channel as well. I'll see you around in the next video. Take care and have a great year ahead. Bye.